All right, let's do this. So number 1 for exam 2, oxidation states of carbon. So are there any questions on that? No, but I'll go over it anyway. It's kind of easy. So carbon, right? Oxidation states, you know them for, is a rule, is a chart for the rules. So for hydrogen, it's always +1, so you're gonna have +5. Nitrogen, sometimes it changes, but if you don't, it might be plus, it's usually +3 or +5, or -3 or -5, but in this case it's -3. How do I know? You really don't, but you're being asked for carbon, so you're gonna guess it's gonna be something. It's gonna be something that we know. It's straightforward, like an ion. So nitrogen will be -3. Hydrogen will be +5. I mean, each one will be +1, but together they'll be +5. That means carbon would have to be -2 to make that cancel out. So the answer would be E. All right, what about number 2? Are there any questions on it? Precipitations. Which one will be precipitation when they mix? You could either answer it, or if there's no other questions, and Adi, no, there's not a rule that makes N equals -3 for oxidation all the time. Sometimes it does. If the problem is asking for a specific element that's not nitrogen, then nitrogen's -3. That's a weird way to say it, but that's usually how it works. So in some cases, like NO2 minus, right? NO2 minus, the oxidation state of nitrogen is plus 3. Plus 3. Wait. Yeah, +3, because -4 + 3 is -1. Yeah. Okay. So solubility rules. Anybody need anything? So if you flip, anytime you see lead, mercury, or silver, it's most likely going to be not soluble after it flips. And you flip these two for D. You flip them, you get lead chloride, which is not soluble. What about number 3? Strong electrolyte, weak electrolyte, all that stuff. So strong electrolyte is going to be strong acid, strong base, ionic salt. So out of those, which one is it? A, nice, good. HCl, hydrochloric acid. All right, which of the following solutions has the greatest sulfate ion concentration? So we're looking at the ions themselves, where in this one, they're all the same volume and molarity, so we don't have to worry about that. And we just need to look at sulfate ions. So this one has 1, this one has 1, exactly. C has 3 sulfate ions, so C is going to be your answer. Good. Number 5 should be D. Wait, no. No, it should not be D. Well, no, concentration. Well, even if it was percent. So the reason why they give you the same number, same amount, because this means you have the same amount of moles of each molecule. So it's keeping the moles constant, because you can get moles from the liters in the molarity. So the moles are constant, but the sulfate per mole of the molecule is changing. So the one with the most sulfates should be the answer. Yeah, but there's 2 Fe. Yes. Yes, it doesn't matter. I mean, it could be a ton of everything. Like, I see what you're saying. It's not it's not percent. Right. So you could say, like, for D, there'd be 2 times the amount of sulfate. I see what you're getting at, than Mn, than manganese. But at the same time, concentration is very absolute. So it depends how much of the stuff there is in the amount of liquid. Yeah, exactly. Concentration is how much there is. You always, so in my research, I always learn to think about concentration as amount, because we're never changing the volume. In an experiment, we're not really changing the volume ever. Just concentration is the amount of stuff that's in there. And you can have 15 different concentrations of other things. It doesn't lower other concentrations. You could just have multiple concentrations of different substances. So, Okay, 5. A 10 milliliter solution of 0.1 molar NaCl is added to 10 milliliters of 0.2 molar KCl. What is the concentration of Cl ions in the final mixture? All right, here's a good one. Has to do with concentration, right? Amount. So in this case, what you would do is you can use the 10 milliliters of 0.1 molar NaCl to calculate the moles. And the way you would do that, using the molarity equation, you would take 0.1 molar times 10 milliliters in liters, which is 0.01. And that gives you 0.001 moles. Then the same thing for the KCl, which is double of that, which would be 0.002 moles. So that means your total moles are 0.003. Since you're adding these mixtures together, or these solutions, you're going to divide the moles by the liters. And now the liters is the combination of both volumes. So that's going to be 20 milliliters. And your answer is 0.15. Does anybody have any questions on that one? So again, it's when you're dealing with concentrations, if you can figure out amount, that's great, because amount is absolute. So you figure out the amounts first, the moles, then you can add those moles up, divide by your final volume of the mixture put together, and you get your molarity. Okay, next. In the reaction below, which element is getting oxidized? So oxidation reduction is a lot of things you have to look for. I would say the first thing is to assign everything oxidation states, because that is fun to do, and also it will most likely tell you the answer or not. Or if you want a quicker way, you can just kind of look at things like which one gains or loses electrons or oxygens or gains hydrogens, but it might not be as easy to figure out. So for example, if you look at this one, As2O3, the arsenic has three oxygens. You go over here, it has 4 oxygens, but it also gained hydrogen. So how do you know if it is oxidized or reduced? This is why the oxidation state number is the best way to figure it out. All right, so we can calculate all of these. So oxygen's -2 in all cases. Nitrogen in this case for HNO3, and here's a good example where nitrogen changes, is going to be, since hydrogen is +1, that means it would be +1 -6, it's +5, or it's -5. Nitrogen is +5. Nitrogen over here is only +2. So going from +5 to +2, that means nitrogen is what? Oxidized or reduced? If it goes from +5 to +2. Anybody? If nitrogen goes from +5 to +2, is it oxidized or reduced? No, the opposite of that. Yeah, reduced, right? Because so reduced means you're gaining electrons. Remember oil rig, gaining electrons. Reduction is gaining, right? So that means the oxidation number goes down. You're gaining negatives. Remember, these electrons are negatives, so you're gaining them. Then for, yeah, it's a flip-flop. Reduction is gaining, oxidizing is losing. When you oxidized, the oxidation state increases. So it's not nitrogen. So let's look at arsenic. Arsenic in the left side, we have -6. That means arsenic would be +3. Over here, we have -8 +3, which is +5. Or sorry, -5. That means arsenic is +5. So we went from +3 to +5. That is oxidized. So arsenic is being oxidized. Any questions on that? No? All right. All right, so iron is produced from its ore in the reaction. How many moles of O2 are needed to produce 4.6 moles of Fe? So this is our first taste of stoichiometry. So it's very important. Stoichiometry is hugely important for most chapters, as we saw. All right, so O2 to create Fe. Now let's follow O2. So 1 mole of O2 reacts to make 2 moles of this. 3 moles of that reacts with iron oxide to make 1 mole of Fe. So so we got to figure out, we got to backtrack. The best way to do this is to do it backwards. So 4.6 moles of Fe. We know that 1 mole is produced from 3 moles of CO. That means to get from the Fe to the CO, 1 mole here, 3 moles here, the best thing is to multiply it by 3. So we get to do 4.6, which is the amount of Fe, and multiply that by 3. And we get 13.8. So now we know that 4.6 moles of Fe is produced by 13.8 moles of CO. So now we can go back and we can see, all right, we have 13.8 moles of CO. And we can take that CO, we can go back here to the first equation. If we have 13.8 moles of CO and 2 moles makes 1 mole, or is produced from 1 mole of O2, then we can just divide it by 2. So we take the 13.8 and we divide it by 2, and we get 6.9. So that means 6.9 would be the amount of O2 that is needed to produce the required amount of Fe. It's kind of going backwards in stoichiometry. Oh, damn. Wait a minute. Adi made a good point. The second equation is not balanced. Ooh, tricked me. All right, cut. Ooh, yeah, it's tough. Not balanced. Yeah, so you balance it, then you do that. Okay. So the way you would balance this, you'd put a 2 in front of the Fe. And then you have 6 of these. You put a 2 in front of the Fe, 3 in front of the CO2, and that would work. Yeah, so the real answer, let's see, 4.6. If 2 is responsible for 3, you multiply that by 3 over 2. That'd be 6.9 moles of CO. And then 6.9 moles of CO would be here. The first one's balanced. And then you would divide that by 2, and you get 2.3. Or no, 3.5. Yes. Yep, so the answer would be 3.5. Good job, Adi. Okay. 8, consider the fermentation reaction of glucose. You have the reaction there and make sure it's balanced, and it looks like it is. All right. So that's sneaky of them to put coefficients in an equation that's not fully balanced. Very sneaky. Very sneaky. Okay. So we have 180 gram sample of C6H12O6 was placed in a vat with enough yeast to start fermentation. If 32.3 grams of C2H5OH was obtained, what is the percent yield? All right. So we have 180 grams and it started the fermentation. So we know our theoretical yield is based off of 180 grams, and we can calculate that. So we can calculate the molar mass of C6H12O6. That would be 6 times 12 plus 6 times 16 plus 12, which is 180. So the molar mass is 180, and we have 180 grams of it, which means we have 1 mole. So if we have 1 mole, we know that's supposed to create 2 moles of C2H5OH. The molar mass of C2H5OH is 24 plus 6 plus 12, plus 16. That's 46 times 2, which is 62. So we know the intended molar mass is 62. Wait a minute. Nope, not 62. Hold on. Hold up. I didn't put my parentheses. 24 plus 6 plus 16. That's 46 times 2, 92. So if we're supposed to get 92, but we only got 32.3, our answer is 35% yield, 35.1% yield. So that's going to be A, which isn't terrible. I mean, depending on the reaction you're doing. Fermentation, that's a pretty well-studied reaction, so you should get more. Maybe they were a sloppy chemist. But okay, any questions on that one? I know percent yield might be a topic of interest for some of you. No? All right. Next, number 9. So a standard Poland Spring water bottle holds about 500 grams of water. If this water is heated up and converted to steam at 100 degrees Celsius and 100 atm, what will be the volume occupied by the steam produced? Okay. So we have to use, if they give you that R constant, PivNert. You would solve a PivNert with 1 atm as the pressure, V as the volume is unknown, N is the number of moles of water, which we have 500 grams. 500 divided by 18 is 33.3. And then we have R, which is our constant, which is given, and then temperature, which is 100 Celsius plus 273 or 373, and we'd solve for volume. Any questions on that one? No? All right. So here's one. A gas occupies that many liters at a temperature of 278. Calculate the temperature at which the volume will be 3.63 liters. And they give you that R constant, but you don't actually need it here. So what we do is we can use Charles's law, because Charles's law depends on the volume and temperature. So we know V over T, V1 over T1 equals V2 over T2. We have our V1, which is 3.42, and our T1, which is 278 Kelvin. That's going to equal our V2, which is 3.63, divided by our T2, which is unknown. And then we can solve for that, and we get our answer. Remember, the temperature always has to be in Kelvin for these gas laws because of our constant, and not even because of our constant, because of the multiplicity. So 1 degree Celsius compared to 2 degrees Celsius, it's double. But 273 compared to 274 is not double. So we always need to have it in Kelvin. All right. Going on number 11, you place 1 mole of H2 gas and 1 mole of HE gas in 2 balloons at STP. Remember, STP is our standard temperature pressure, and it is 1 atm, 0 degrees Celsius. The 2 balloons will have the same blank. All right. So the only difference here is the molecule that's in the balloon, or atom that's in the balloon, hydrogen gas versus helium gas. Helium gas is heavier, has a molar mass of 4. Hydrogen gas is a molar mass of 2. What's the same? So the volume and the average kinetic energy would be the same. I don't know. The average kinetic energy and the density and the velocity, the pressure and the velocity and the average kinetic energy. So let's talk about volume first. We'll just talk about each one of these factors as they come up in the question, in the answers. So volume, since one thing about ideal gases is that they're so small, the individual molecules are so tiny that we don't consider them to be taking up any volume that's different than other gases. So for all intents and purposes of ideal gases, H2 will take up the same space as O2 even. So the volume will be the same. That's true. Then let's look at average kinetic energy. So average kinetic energy means the average speed of them. Or no, it means the average speed with the mass factored in. The average velocity is going to be different because remember we learned that the smaller gases move faster, but the heavier ones move slower, meaning if we do our 1/2 mv squared, it'll cancel out. And we know that means our average kinetic energy of the gases will be the same. And yes, Adi, that's a good deduct, or a good I don't know. What's the word when you take one subject or one lesson and bring it to another one? I don't know. Whatever. It's a good thing, yes. So that's a good thing that you mentioned, that average kinetic energy is just the temperature. That's what we learned in chapter 1. Temperature is just the measure of the average kinetic energy of the particles. So it makes sense that if the gases are there at a certain condition in temperature, that they're and also the pressure and everything else is held constant, then the average kinetic energy will be the same, regardless of their size, because that's accounted for mass. But the velocity will be different. So the hydrogen will have a faster velocity because they're lighter. Then we talk about density. So density will be larger for helium because they take up the same amount of space. They have the same volume, but helium will be heavier because its molar mass is 4, where hydrogen it's 2. And then pressure, the pressure is going to be the same because it's STP, but the velocity is going to be different because I said that before. But yeah, that's a good question. Okay, next, number 12. CO reacts with oxygen according to this equation. If the initial partial pressures of CO and O2 are both 1.5, what is the total pressure at the end of the reaction? Now, this one's kind of tough. So here's what I think, or here's what I this one being on the final, I don't know. I don't think it will be, but I'll tell you how you do it. Now, you can kind of make pressure akin to amount, because if you take away the volume, right? So think about PV equals nRT. You take away the temperature. Let's make it's all in the same vessel. So temperature is the same. It's constant. The number of moles are a number of moles. R is a constant. The volume, since it's in the same vessel, is a constant. You cancel all of those things out. You have a relationship between P and N. The pressure is somehow proportional to the moles. We can deduce that information from PV equals nRT and take that into this question. So we can say that if 2 ATM of CO reacts with 1 ATM of oxygen, you get 2 ATM of CO2. That is valid to say if they're in the same container at the same pressure at the same temperature. Or no, at the same, not same pressure, at the same, whatever. Every condition is the same except for pressure. We can say that because their pressure would be the thing that determines their amount because everything else is held constant. Okay, and the same is true if you had the pressure constant, the volume of each of the gases would be able to determine its amount. Okay, so what is the total pressure at the end of the reaction? So let's see, it's the initial partial pressures of CO and O2 are both 1.5. How much will it make? So we know 2 of CO, 2 ATM of CO reacts with 1 ATM of O2 to make 2 ATM of this. Here we have 1. That means the CO is limiting because it requires 2 moles. This one would run out first. If you had 1 mole of each, the CO would run out first. So we know that if we have 1.5 moles of CO or 1.5 ATM of CO, that means when it runs out, the 1.5 ATM of O2 will still be there. So what this means is that 1.5 is now R2. And we can rewrite this equation, kind of. So hold on, let me get the pen out. You can't really explain this well. I gotta write it. All right, so we'll put this here. Yeah, okay. All right. Okay, so we have 2CO plus O2 yields 2CO2. They're both 1.5. So we can say that we now have 1.5 CO2 plus, this would now be half of that, so 0.75 O2 yields 1 CO2. So we basically just like, we didn't cut it in half, we cut it into the amount that we have. So this makes it a little bit easier. This is a different approach. It makes it a little bit easier. So now from this, we can say, all right, all the CO2, the 1.5 of CO2 is done. No longer there. The 1.5 of O2 gets reduced down to 0.75 because half of it's gone. So we have this left, and then we have the other half is used. Then the other half that's used gets converted with this amount, gets converted to 1 ATM of CO2. So we have 1 ATM of CO2. So our total pressure of the entire thing after it's done is 1.75. All right. That one was tough, right? Ask questions about it. What did I not explain? I didn't explain it great. So clear things up with me. Wait, there isn't? Oh, I just saw it. What is the total pressure to end the reaction? They're both 1.5. Oh, I'm stupid. I know why. I messed up. Because this is not 1. So for this one, it's not 1. Hold on. So that's right. So I messed up here. All right. Okay. So if 1, this should make double. So this should make 1.5. Right. That makes sense. Okay. Is that better? This would make 1.5. That means if the 1.5 is made, you would have 1.5 ATM of CO2. Add those up, you get 2.25. Yes, exactly. So I just made a mistake with my ratios. Okay, I'm gonna talk about it one more time just to clear it up. Okay, so this is the balanced reaction that's given, right? You're given that there's 1.5 ATM of each one of the reactants, the CO2 and the O2. If that's the case, if we know that 2 CO2 react with 1 O2, then we can say 1.5 of CO2 will react with half of that of O2. That would be 0.75. If we originally have 1.5 of O2, not 0.75, 1.5, then we'd only be using half of the O2 that we are provided with. Therefore, half of it will remain. So we're going to use half remains. We're going to use that half and all of the CO2 to make the same 1-to-1 equivalent of CO or CO2, sorry, whatever, of the product. Let's just say that, of the product. Since the product and CO and the reactant are in a 1-to-1 ratio or 2-to-2 ratio. If that's the case, 1.5 ATM of CO2 will be produced of the product. So we take that 1.5, we add it to the amount of reactant that is still present after the reaction occurs, and we end up with 2.25. Does that make sense? Okay, cool. All right, moving on. That's a difficult one. Moving on. So here we go. So when 0.72 grams of a liquid is vaporized at 110 and that much ATM, the gas occupies that many liters. The empirical formula of the gas is that. What's the molecular formula? All right, so you can do a PivNert, and then you're going to solve for N. And since you have the grams, you're going to say the grams divided by the moles, or the grams divided by the molar mass is the N. And you have the empirical formula. So you can say that you can find the molar mass using N and the grams, since the grams divided by the molar mass equals N, you can solve for the molar mass. Once you solve for the molar mass, you can divide the molar mass by the empirical formula molar mass, which happens to be 14, because it's going to be 12 plus 2. And then that number that you get, it would be a whole number, would be the multiple that you multiply the empirical formula by to obtain your molecular formula. Does that make sense? Or do you have any questions? Or do you want me to go over it? No? All right. Okay, so number 14. 1 mole of an ideal gas is expanded to a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atm. How much work is done in the surroundings? Oh, Adi, good question. So why would it be wrong to multiply the empirical by N? So N would not give you a whole number. Like the PV equals nRT, N would not give you a whole number. That would give you the number of moles that would just give you the number of moles that are in the sample. That wouldn't, or in this reaction. That wouldn't give you a multiple of any type. So the only thing you multiply by the empirical formula by is by an integer that is the molecular formula divided by the empirical formula. Okay, good question. Okay, so how much work in joules? So now remember that formula, and this formula, all the formulas will be given to you. The formula W, which is work, equals negative P delta V. So we're going to be using that here. And you have external pressure of 1 atm. So this would be 1. And you have change in volume, which is what you have. You have, what is it, 8.93 minus 1. So that's 7.93. 7.93. This would be negative. So the work is going to be 7.93. This is going to be liter, or ATM liter ATM. And then you know that 1 liter ATM is 101.3 joules. We want to convert to joules. What else did I tell you? Performed on the surroundings. That's important too. So we multiply this by 101.3 joules to get our conversion. And that should be around, I don't know, 800 something. 803 looks good. So it's probably the answer. Okay, next. Consider the reaction with at constant pressure of that, and you have a negative enthalpy. Click the correct statement, or write the correct statement. Negative enthalpy means exothermic. Energy and heat is being released. So the reaction releases heat. Great. Reaction is not balanced. It's pretty balanced to me. It looks balanced. So yeah, reaction releases heat, not endothermic. It is a redox. Yeah, that's it. So C. All right. So given the enthalpy of fusion, so going from energy to melt ice into water, calculate the energy required to melt 50 grams of ice. Now, the key here is to look at the units. They give you kilojoules per mole. You have 50 grams of ice. How many moles is that? So you do 50 divided by 18. Multiply that number by 6.02 kilojoules per mole to figure out the number of kilojoules. Then here we go again. 50 grams of water at 80 degrees Celsius is added to 120 grams of water at 20 degrees Celsius. The resulting temperature will be where? That's a good question. So basically, since they're both water, we don't have to worry about specific heat too much because the specific heats will cancel out. But we want to see, all right, this is a good conceptual question. You have 50 grams at 80, and you have more than double the amount at 20. That means the equilibrium temperature will be closer to 20 than it is to 80. So a good gap, the halfway point between 80 and 20 is what? 40, 50. Wait, there's 60 units between them, so 50. Yeah, it'd be 50. So that means it would be definitely less than 50. And I would, if I had to guess, I'd say between 20 and 40. So that would be the answer. Because it's not going to be closer to 80. Yeah. If the specific heats were different, then we would do our Q equals MCAT equals Q equals MCAT for each of the substances, which we can do here. Or we could just do 1 Q equals MCAT. All right, number 18, consider the following specific heats of metals. If the same amount of heat was added to 25 grams of each of the metals, which are all the same temperature, same initial temperature, which metal would have the highest temperature? So whichever one has the highest temperature after some amount of heat is added means the one that has, you tell me, the lowest specific heat or the highest specific heat? Lowest, good. Because lowest specific heat means it requires, look at the unit, joules per gram Celsius, meaning it takes not that many joules per gram to move it by 1 Celsius. So that means lead would be the answer. Next, calculate the change in internal energy. That's easy. Internal energy is E. E equals Q plus W. So we have absorbs that much heat, so that means it's going to be a plus Q, and then performs that much on the surroundings, so a minus W. That's why the context is important. So it's going to be 2.4 kilojoules minus 0.2 kilojoules, which would be 2.2 plus 2.2 kilojoules, which is C. That make sense? Okay, next. So for the reaction, if the percent yield is 82%, what is the actual mass of hydrazine produced when 25.57 grams reacts with 4.45 grams of hydrogen? Okay, so this is stoichiometry. If you know it's 80%, you can just find 82%. You could find the theoretical yield. First, you need to find the limiting reagent. Then you need to find the theoretical yield. And then you could say 82% of that theoretical yield is going to be the actual. So does anybody want me to go over that? It has limiting reactant in it and other things like that. So if so, let me know. Does anybody want me to go over this one? Don't be shy. All right, 3, 2, 1. Nobody. All right. All right, next one, number 2. What volume of that amount of sulfuric acid is required to completely react with that stuff? All right. Now, this is an acid-base reaction. Make sure it's balanced, which it's not. So, here. This is a similar one. Hold on. Where'd my pen go? I dropped it. And now it's, oh no, it's right here. All right, so this is a similar one, but does anybody want me to go over it? I mean, again, it's stoichiometry, but if it's, I mean, it is an important topic. But I mean, we did cover it a lot, but it is an important topic. And if anybody wants me to go over it again, I'd be happy to. Does anybody want me to go over this one? Number 2. Oh, yes. Okay. Thanks, Alex. All right. So make me feel like I'm doing some kind of work at least, but thanks, Alex. All right. So I will erase this. All right. So we have the equation. Let's balance it first. H2SO4 plus KOH. Every acid-base reaction makes water and a salt. So K2SO4 is the salt, and H2O is the water. Now, to balance it, we have H2. Here we have HOH, so we need to put a 2 in front of there, 2 in front of here. Sulfates are good, and we're good. Next, we want to see what we're dealing with, how much stuff we're dealing with. So we have, what is the volume of 0.1 molar sulfuric acid required to react with 20 milliliters of 0.15 molar? All right, I see that. I'm automatically thinking for the KOH, I'm thinking find the moles because you're going to need that. So 0.150 molarity equals X over 0.02 liters. All right, so now we multiply and we get 1 second, 0.15 times 0.02, 0.003 moles. Okay, so if we have this many moles react, how many moles of H2SO4 is required to react with that? So if we have 1 is required to react with 2, then half of 1 would be, or sorry, half of, well, if half of 2 is required to react with 2, then half of 0.03 is required to react with 0.03. So that means for H2SO4, we need 0.0015. Does that make sense? I'll stop right there. That's the hardest part, to figure out how many moles of acid you need. So you're just using the ratios from the equation, from the balanced equation. Good. All right. So then after that, you just use the information they gave you on that sulfuric acid, which is it's 0.1 molar. So 0.100 molar equals 0.0015 moles, which we just figured out. And the question is asking for the volume. So we can divide it by X liters, and we can do that, and we get 0.0015 divided by 0.1, which is 0.015 liters, or 15 milliliters. Any questions on that? So basically, you're setting up the equation, doing stoichiometry, and figuring out how much moles you need. Good. All right. So next, number 3, if you have a 10-liter helium tank at 12 ATM, what is the maximum number of 2-liter helium balloons that you can fill with your helium tank at STP? Now this one's tough. So I did talk about, 1 second. My cat wanted me to throw, she plays fetch, so she wanted me to throw something and she was bothering me. So I threw it for her. All right. So you have the tank problem. So the tank problem is different. We're going to go over this one because you may get it. And I don't want you to be thrown off with tanks. All right. So for tank problems, I did talk about, this was more than a month ago, that when you have a tank that's pressurized, not all of the gas will be removed from the tank when it's empty. When a tank is empty, that means the pressure inside the tank has reached equilibrium with the pressure from the outside world, which means there's no pressure gradient from high to low pushing the gas outside of the tank because there's no other forces going on. It's just the pressure gradient is the force. And once you remove that pressure gradient, there's no more net movement of gas. So what we do here is we can say we have a 10-liter tank that's 12 ATM. And the balloons are how much? 2-liter balloons. So 2-liter balloons. And what is the maximum number of 2-liter balloons you can fill at STP? So we want our balloons to be STP, which means our ATM is 1 ATM for our balloons. So if we want this to be 1 ATM, what are our real liters? Or that's not a good question. So if we want this amount, so here, PV, right? All we're doing here is very similar before. In the question from earlier in the test, we had the P pressure was basically akin to an amount if we kept everything else constant. In this case, a PV is equal to an amount. PV is equal to N if R and T are constant. So if that's the case, then we can say our PVs are our amounts. So our PV I'll write initial PV equals 1200. So it's the pressure times the volume. Then each balloon PV equals 2. But we can't use all of these all of these 120. I said 1200, I meant 120. I can't use all these 120s and just divide it by 2 to see how many balloons, because you need to have a certain amount of ATM, you need to have 1 ATM left. Now, since the volume of the container is 10, you need to have left over 10 liters times 1 ATM. That is the amount that's going to be left over in the tank. So it's going to be 10 PVs. So PV left equals 10. Final PV, or usable, we'll call them usable PVs, equals 110. So 110 of your PVs are usable, because the other remainder has to be in the tank, because that's when it reaches equilibrium with the outside atmosphere. So we can take this 110 and divide it by 2, which means we can have 55 balloons. Okay, does that make sense? And are there any questions? No? Okay, moving on. Next, number 4. Combustion of that much benzene causes the temperature change of 3.29. What is the heat combustion per mole? All right, so basically for this one, we're not going to go crazy, but what you can do is you're going to use your Q equals MCAT, which is going to be given. 1 second. So your Q equals MCAT is going to be given. Q equals MC delta T. You have, in this case, you have your mass, 2.82, times your temperature change and your calorimetry, which is 3.58. Well, we don't even need mass here, because we're not doing our constant is based on kilojoules per Kelvin or per Celsius. So we're going to do, hold on, no. So it would be, in this case, it would just be Q equals C delta T. So 35.8 times our temperature change, which is 3.29. This would give us our Q for this amount, for the amount of 2.82, because it tells you the temperature change and the constant. So you multiply those together. I guess we'll do this one. Why not? 35.8 times 3.29. You get 117.78. And this is going to be your joules per 2.82 grams. Now, if you're doing per mole, benzene has a molar mass of 180. Or no, of 80, not 180. So 2.82 divided by 80. 0.82 divided by 80 is 0.035 moles. So if 0.35 moles releases this much energy, we can do joules per mole and do that. So it'd be 117.78 divided by 0.035, and you get 336 kilojoules per mole. Okay. All right. Any questions on the second exam? Nope. All right, cool. All right, I'm going to end this video.